Okay, guys, let's take a look at a series and we want to decide if it converges absolutely, conditionally, or diverges. So first, let me just remind you what those mean. And this absolute or conditional convergence only works with series that have some negative terms. Otherwise, it doesn't make sense. It doesn't matter if it's going to be absolutely or conditionally. What happens with series that have negative terms? In particular, a lot of times this concept is used with alternating series, like -1 to the power n or -1 to the power n plus 1. You will see a term like that. So with these types of series, what you do is you first check to see if absolute value converges, because there is a big result, and it's like a theorem, that if absolute value converges of your series, what that means is that if you were to apply absolute value and that would converge, then automatically the one without the absolute value will also converge. So you don't have to do it again. Like if you already showed that absolute value converges, then series just converges absolutely and that's it. So you don't have to check the second step. However, if absolute value does diverge, if absolute value series diverges, then you have to check the original series. Then you have to go back and decide, okay, what about without the absolute values? Maybe it will converge. If it does, then it's called conditional convergence. If it doesn't, that just means it diverges and that's it. So let's see what happens in this particular case. Okay, so we're going to start with this one. And step one, we're going to say, okay, well, maybe the absolute value series converges. So how do I find that? Well, I apply absolute value to my series. Now, because 3n being a 1 to 3 integer, so on, that's positive, and n squared plus 2 is also positive. The only thing that could be negative is this -1 to the power n. But what is that? Well, that's the term that is responsible for alternating signs, because when n equals 1, you get -1 to the power 1, which is -1. If it's n equals 2, then it's going to be -1 squared, which is +1, and so on and so forth. So it'll switch. For all odd n's, it's going to be -1. For all even ones, it's going to be +1. But regardless, absolute value of -1 is 1, and absolute value of 1 is 1, and multiplying by 1 does not change anything. So basically what that means is that the absolute value will just get rid of that -1 to the power n. So we are considering just this guy. Okay, what kind of test will you use to prove whether this series converges or diverges? When you have a series with positive terms, what can you do? Well, you have choices. First of all, you could say to yourself, okay, maybe divergence test, because divergence test is very easy. And divergence test says that if you take the limit of the nth term and that is not 0, then the original series diverges. However, if I try to do that, then remember how all the terms that are not highest powers can be discarded. So you've got 3n divided by n squared. And what is that in the limit? Well, 1n is going to cancel. So you're going to get 3 divided by n. And 3 over infinity. So remember, number over infinity is 0. Does that help? No, it doesn't. So a very common misconception is to try to use divergence test. And if the answer is not 0, say diverges. But if the answer is 0, say converges. That's completely not true. Okay, then you wouldn't need any other tests if divergence test was such an easy test to use. So this is a false start. This means that this is not a good idea to do that. Another false start would have been a ratio test, which I don't want to show here, but if you were to show, if you substitute n plus 1 for n and divided them and you evaluate the limit, the answer would have been 1. And that's also inconclusive. So for ratio test, that's really not good. What you should know is that when you have a fraction of polynomial divided by another polynomial, then this is what we call limit comparison test. So this is limit comparison test. It's a classic example. So what does that mean? It means that we have to study the behavior of the nth term when n is large. And we know, so I draw that like symbol. So this stands for like a tilde, like. This guy is like what? Well, just drop the plus 2 because it doesn't matter at infinity and simplify. So very important, you can't stop here, you have to simplify. So this is n to the power 1. We are subtracting the powers. We keep in the n wherever is the larger of the powers. So this is going to be 3 divided by n. Now, what kind of series is 3 divided by n? If you were to take out the 3, which you can always do out of the series because that's a multiple, you're going to get 1 over n. What kind of series is this? This is a p series with p equals 1. In fact, it has a special name. It's called harmonic series. So harmonic series is a very famous series where the nth term does go to 0, 1 over n approaches 0, but the series will diverge. So this guy is divergent, and then by the limit comparison test, that means that the original series also diverges. Now, if it was somebody else other than me, okay, teaching you calculus, then this person will for sure ask you to show why these two series are like each other. So I already said divergence. But how do I know that 3n divided by n squared plus 2, how do I know it's 3n over n squared when n is large? Yes, I can make an argument and say, well, who cares about the plus 2? But that's kind of like, well, no, you have to prove it. So the teacher will probably ask you to prove, and the way you prove it is you have to take the original series that you're comparing with another series and divide by that series. And usually it's better to not simplify it at this point and just say 3n divided by n squared. And then show that that limit is not 0 and not infinity, which is actually super easy. If you were to just flip the fraction, this is going to be n squared, this is 3n. Now, I can cancel the 3n. And again, if your teacher is nice, it'll say, well, who cares about the plus 2? But okay, let's say you really want a formal proof of it, then divide the numerator and the denominator by n squared. So if you were to divide here by n squared, here by n squared, and here by n squared, what do you get? Well, n squared over n squared is 1. Here it's going to be 1 plus 2 divided by n squared. And hopefully at this point your teacher will be okay with you saying that 2 over infinity is 0. So the answer is 1. Okay, so that is not 0 and not infinity. We just showed that these two series behave like each other, even though we knew that was right. But okay, this is a formal proof. But they are like each other. So that means that the absolute value series converges. I'm sorry, diverges. Diverges, because it was like harmonic. Okay, that's bad news. Why is that bad news? Because if at this point you said it was convergent, you would stop. You would just say, okay, the original series also converges by this big theorem that says if the absolute value converges, the original one also converges. So then you would say, okay, the original one converges absolutely, nothing else I gotta do. Unfortunately, that did not happen here. We compared our series with the divergent series, and our series diverges. So what does that mean? It means that you have to go back to the original series and investigate that. Maybe that one converges. Okay, so then what choices do you have? Now, we already know, by the way, we already showed that 3n divided by n squared plus 2, the limit is 0. We already showed that. We know that. That means that we're supposed to use alternating series test, because for alternating series, where you have some kind of like p series term, this kind of thing is like p series, you want to use either alternating series test to show convergence or divergence test to show divergence. How do you know? Well, you have to take the limit of whatever I just highlighted. So this is 3n divided by n squared plus 2. If that limit is 0, you are basically almost done. Almost done. You checked condition number 1. You did check it. Again, you could divide everything by n squared. And you will see that it's going to be like 3 over n. That goes to 0. So anyway, this limit is just like this. In my book, I'm okay with that kind of proof, and this is just going to be 3 divided by n, which is 0. Okay, check. So that's condition number 1. The limit is 0. And alternating series test also says that you have to prove that this sequence, the 3n divided by n squared plus 2, it is a decreasing sequence. Now, just to kind of point out what does that mean decreasing sequence. If you were to enter something like a sub n equals on the top 3n over n squared plus 2. If you were to try to compute a of 1, then look at a of 2, a of 3, a of 4, a of 5, and so on and so forth. You can see something happening. As n increases, the value of the series, right, goes down. Now that means it's decreasing. Now, that did not happen right away. And sometimes with these series, it doesn't happen for the first couple of terms, or maybe even the first 100 terms. It doesn't matter. As long as eventually they become decreasing, that's what matters, okay, for this test. Eventually, the terms will just go down. So this is really not a proof. This is a very important conceptual thing here, that you can't just because A5 and A6 satisfy the requirement that the sixth term is less than the fifth term, and the same thing will happen to a 100th term compared to 101. Yes, maybe it satisfies, but what if later on it starts to fail? So this is not a proof, okay? So to prove it, my preference is to consider a corresponding function. So I'm going to go with f of x, which is 3x divided by x squared plus 2. And there is a problem with this function showing that it's decreasing because it does require you to know some rules of differentiation. Unfortunately, you do have to know what's quotient rule. It is not correct when you take the derivative is to take the derivative of the numerator and then divide it by the derivative of the denominator. That is completely wrong. But why derivative? Like, what are you talking about? Because there's a connection between the derivative and the original function. So remember, if the derivative is negative, that means that the slope, because derivative is the slope of the curve at a point, if the slope is negative, then the function will go down, basically. So we do have to find the derivative of a fraction. And for that, I have a son that I remember, so I could remember the quotient rule. It's called the high-ho song. Okay, so this song says that here's how it looks like. It's going to be ho d high minus high d ho over ho ho. Okay, so it's like a Santa Claus song. Okay, so what's that mean? Well, d high means derivative of the top, and d ho means derivative of the bottom. Okay, so let's use this rule to find the derivative. Okay, so on the bottom, ho ho ho, we are just squaring the bottom and leaving it alone. Okay, just square it, leave it alone. Never try to distribute the square to each part because this is not correct. This is actually x squared plus 2 multiplied by x squared plus 2. But the whole point is to actually show this is going to decrease. You do not want, in other words, the derivative will be negative. You do not want to mess with the bottom because now you can see the bottom will not determine the sign. The bottom is always positive because it's an expression that is squared. Okay, so what's on the top? Well, that's ho, which is x squared plus 2, d high, derivative of the top, which is 3, minus high, which is 3x, derivative of the whole, which is x squared, plus 2, which is 2x. Okay, do not try to divide x squared plus 2 with the top and the bottom. That is so bad. It's a very bad mistake. You cannot ever simplify it like that. Just trust me. Don't touch the bottom. Don't you touch that, okay? Because that's a bad idea. It's algebraically not correct because you also have this other term here. So what should you do? Well, you have to simplify this. So we're going to go ahead and distribute this. This is going to be 3x squared plus 6 minus 6x squared. Continue simplifying this. So this is going to still stay x squared plus 2 squared on the bottom. On the top, I need to combine like terms. So 3x squared minus 6x squared. That is negative 3x squared plus 6. So, like I was telling you, this guy is always positive. So I want to make sure that the top is negative when, well, at some point. Now remember, we're talking about series, so we're not talking about negative values of x. We're talking about x greater than or equal to some number. Really doesn't matter if it's 1. It doesn't have to be 1. But at some point, this should work. So if I want to solve an inequality, negative 3x squared plus 6 negative, How do I do that? Well, I'm going to subtract 6 from both sides. So this is going to be negative 3x squared less than negative 6. I'm going to divide both sides by negative 3. Now, remember when you're dividing an inequality by a negative, that will flip the sign of the inequality. So this is x squared is actually going to be greater than 2. And then you can take the square root, remembering that x is a positive number. We're talking about series, nothing negative. So x is going to be greater than square root of 2. Now, square root of 2 is approximately 1.4 something, and x should be an integer, so it has to be greater than 1.4. So I think starting with 2, this is going to work out. Okay, so we are going to enter this negative 3x squared plus 6 divided by x squared plus 2 squared. And starting with 2, this is going to work. Now, if you don't believe me, you can just literally plug this into the calculator. Only the top. You don't have to plug the whole thing. So let's just say g of x equals negative 3x squared plus 6. Eventually, it'll start being negative. So if you try 1, no, it's not. If you try 2, yes, it is. So starting with 2, it is going to be negative. So everything else, like once it starts being negative, it's going to continue being negative. So starting with 2, which is perfectly fine. The first few terms do not make any difference in terms of convergence or divergence of a series. So we just showed that by alternating series test, the series converges. So what does that mean? The absolute value series was divergent, but the original series was convergent. That tells you that the series converges conditionally.